Welcome to June's Leetcode Challenge. Today's problem is construct binary tree from preorder and inorder traversal. Given two integer arrays, preorder and inorder, where preorder is the preorder traversal of the binary tree and inorder is the inorder traversal of the tree, which just goes left to right, construct and return the binary tree. So we're given two lists, one with a list of numbers in the preorder and one with a list of numbers in the inorder. Now we want to build our binary tree in accordance to both of these. Both of them are guaranteed to be correct, but the key thing to note here is that preorder and inorder consist of unique values. And the reason that's important is because we already know that we want to build this tree in preorder. But the problem is, all we have is a list here, so we don't know when to stop building like from the left to right. We know that this 3 here is going to be the root, and this 9 that comes next, does that go on the left or right? And we have no idea. So to do this, what we'll have to do is kind of break this up into sub-problems and use this inorder here to kind of determine whether we want to continue on the left and right. So what I mean by that is, let's just say that we had two binary trees. Both of them have the preorder of 1, 2, 3, right? One has 1, 2, 3 like this, and the other has 1, 2, 3. And they're both technically preorder 1, 2, 3, but the inorders are going to be different. Inorder here is going to be 2, 1, 3, and inorder here is going to be 1, 2, 3. So what we might do is say we start with a preorder. We know we're going to go with this preorder here to build up our tree. We start with 1. Now let's take a look at the inorder. What we'll do is, since this value is distinct, we'll take whatever exists here on the left side and whatever exists on the right side to recursively call like a subproblem here. So here with 1, we can see there's nothing on the left side, right? So what that means is we don't need to build anything on the left. So we can just skip that. So it's almost like we're going to take this 2, 3 here and use that as our next inorder to determine how we're going to build our next subtree. So let's just take a look at our example here. I think it'll make it a little easier to understand. So say we had our preorder and inorder like this. So we already know that we're going to build up our tree starting at the root in the preorder. So that starts with 3, right? Now where's 3 here? Well, on the left, we know everything that comes up to the left of this 3 is going to be on the left side of this tree here, right? So at this point, this would be like 9. Here, everything on this side is going to exist on the right side. Now, since we've already built this preorder here, we can move on to the next number. We can use a Q perhaps and pop that off. Now 9. Do we see 9 on this left side? We do, right? So we'll use this as the next inorder. First we'll pop off 9 here and build the root like this. And next, what was on the left and right side of that? Well, there was nothing, right? These would just be empty. So here with the left and right, we just skip it. We just say, okay, these are both none. We'll just like recursively call these nuns here. Say these are just nuns. And then we move up to the right side now, because the next side is going to be 20. So here we see 20 exists in the middle. So we have to recall this 15 to the left side of 20 and pass the 7 to the next side here. So this would be built like 20. And we pop that off. Next we know 15 comes next, and we have something here, so we add 15 here. And then we add 7 here. So I know that was kind of confusing, but yeah, and keep in mind, if we don't see anything to the left and right of that inorder, then we could just make these both nuns. So these would just be both nuns to the left, like something like that. So that's it, and this is what it would look like, right? It would say 3, 9, 20, 15, 7. 3, 9, 20, 15, 7. And yeah. And so instead of passing in like an extra list every time, that might reach like a memory limit exception, we're just going to pass in pointers. Okay, and whenever we find that the pointer, the start and the end of the pointer is equal, or the start is not less than, or I should say the end is greater than our start, we know there's nothing there, so we can just make that a none. And that would be it. So let's begin. We'll first initialize the preorder into a queue. So what I'll do is make this into a dequeue. And this will make it a little easier to pop things off. I mean, I could certainly just use an index pointer to move ahead whenever we find that we're moving ahead in our recursion, but it just kind of got confusing, so I'm just going to use a queue here. N was going to be the length of either preorder or inorder, doesn't matter. Now we have our helper, so this is going to be our recursion, and we have our start and end. So the first base case condition, if we find that start is greater than end, then we know something's not right, or there's nothing left on the left or right, so we're just going to return none. Now, otherwise, what do we want to do? Well, the first thing we want to do is pop off our candidate from the queue, and we're going to pop left, and we want to build our tree node. So this is going to be the root, and this would be tree node of, and the candidate would be the value, right? Okay, now we want to go left or right. So let's see. Oh, well, the question now here though is we got to find the index point at this inorder to find whatever's left and right. And we can just go through the whole inorder to find that, certainly, but to make that a little bit faster, what I'm going to do is create a lookup, and this is going to be a dictionary. I'll have, let's see, for index value or index and value and enumerate the inorder. We're going to create a lookup for the value and the index point right here. So what this means is we're going to find the middle point in our inorder array. The middle point is going to be lookup candidates, and we will now set our root.left to equal recursion. What do we see? The left side would be the start to the middle minus 1, and the right side would be recursively middle plus 1 to the end. Finally, return the root. I actually think I can just do that here, and that would be it. So all we have to do now is just return our recursion, starting with start of 0 and starting with n, but make sure minus 1 here because our index pointer will make sure it has to be n minus 1. Alright, so let's make sure this works. Okay, that looks like it's working, so let's go ahead and submit. And there we go, accepted. So time complexity wise, it's going to be O of n, because the only, is it O of n? Yeah, it's O of n. We do use O of n space because of this lookup, but otherwise we'll just be doing this like a regular preorder traversal, and whenever we find that the start and ends aren't there, we're going to make these nuns, and we kind of just skip popping off from our preorder, and that'd be it. Now you could certainly avoid doing recursion by using a stack. You can do this iteratively, but what that means is you'll have to end up stacking stuff and then popping it off to find like where the next retrace is, and it just got too messy. I didn't really like it, so I think this is much cleaner and more understandable. But otherwise, I think that's it. This is not an easy question. Like this, I saw this before, but I still had trouble solving it. Yeah, so yeah, I think one day I want to come back to this and do a deep dive. But otherwise, I'm just going to end it here. Thanks for watching my channel. Remember, do not trust me. I know nothing.